This is section 4.3, and we start out with this chart. We have an absolute minimum. There's no extrema here, even though the first derivative is 0. Here we have a local maximum where the first derivative is 0. We can have a local minimum where the first derivative is 0. Here's the derivatives undefined, but we still have an overall, an absolute max. Here, that's just a point of inflection, but the first derivative is 0. And over here, we have a local minimum on an endpoint. First derivative test for local extrema. The following test applies to a continuous function. We can have, let's see, if f prime changes signs from positive to negative, so if the slopes are changing from positive to negative, we have a local maximum. And that's even true if the first derivative is undefined. If the slopes change from positive to negative, we have a local maximum. Here, they're going from negative to positive, so we have a local minimum. If f prime does not change signs, then we don't have an extrema at all. So if f prime is 0 there, but the slopes go from positive to positive, then there's no extrema there. And this, we can go from negative to negative, no extrema at that one either. And then we can have local maximums at left endpoints, local minimums at left endpoints, local minimums there, and a local maximum at that right endpoint. Using the first derivative test, for each of the following functions, use the first derivative test to find the local extreme values. Identify any absolute extrema. So on letter A, let's go f prime of x is equal to 3x squared minus 12. We're going to set that equal to 0. And we get 3x squared is equal to 12, x squared is equal to 4, x is plus or minus 2. So now those are potential mins and maxes. We're going to throw that on a number line. We get negative 2 and 2, and those are the potential mins and maxes. So we'll test negative 3, 0, and 3, and we're going to plug that into the first derivative. So negative 3 into the first derivative is 27 minus 12. Well, that's positive, so the function is increasing. When we plug 0 in there, we get negative 12, so then the function's decreasing. 3 in here, and that's positive, so the function's increasing. So we have a local maximum of, and it says identify, let's find the local extreme values. So we need to plug that in, and we can even say at x equals negative 2, even though it doesn't really ask where. And then we have a local minimum of something at x equals 2. Now I know this is a maximum because the function increases and then decreases. In other words, the first derivative goes from positive to negative, and then the derivative goes from negative to positive. Well, if we plug negative 2 into the original, I get negative 8 plus 24 minus 5, 16 minus 5, I'm getting 11. And then when we plug, what did I plug in? Negative 2? Yeah, that's right. If I plug 2 in, 8 minus 24 minus 5, that's negative 16 minus 5, I'm getting negative 21. G prime of x on this one is first times the derivative of the second plus the second times the derivative of the first. And we can factor out an e to the x, and we're going to set it equal to 0. So x squared minus 3 plus 2x. So we have e to the x, and I have x squared plus 2x minus 3. That's how we're used to seeing that polynomial there on the end. And this factors into x plus 3 and x minus 1. So we have x equals negative 3, x equals 1 for some critical points, potential mins and maxes. Let's put that on a number line. 1, oh yeah, we have negative 3 and 1. So there's potential mins and maxes. Negative 4, 0, and 2 is what we'll test. If we plug negative 4 back into the first derivative, how about we plug it in right there? Negative times a negative is a positive. If we plug 0 in, positive times a negative is a negative. And if we plug 2 in, positive and a positive is a positive. So we have a local max of well, if I plug negative 3 all the way back in the original, 9 minus 3 is 6. So 6 over e to the third, because it's e to the negative 3. And that's happening at x equals negative 3. Then we have a local minimum of, if I plug 1 in, we get negative 2e at x equals 1. As you can see in figure 4.22, the function y equals x to the third rises as x increases, which means as we go left to right, this function increases the entire time. But the portions defined on the intervals negative infinity to 0 and 0 to infinity turn in different ways. Now what they're saying is that this graph is concave down and then the graph is concave up. It's turning differently. Looking at tangents as we scan from left to right, we see that the slope y prime of the curve decreases on the interval negative infinity to 0. So we have steep slopes, and then as we go left to right, the slopes are decreasing in value. And then increases on the interval 0 to infinity. So once it hits 0, now these slopes are increasing in value. The curve y equals x to the third is concave down on negative infinity to 0 and concave up on 0 to infinity. The curve lies below the tangents where it is concave down. So wherever a function is concave down, the tangent lines will lie above. Wherever a curve is concave up, the tangent lines will lie below. Now it says definition, concavity. The graph of a differentiable function is concave up on the interval I if y prime is increasing. In other words, if the second derivative is positive, that means the first derivative is increasing. Concave down on the interval if y prime is decreased. In other words, y double prime is now less than 0 if y prime is decreasing. The graph of a twice differentiable function y equals f of x is concave up on any interval where the second derivative is positive and concave down on any interval where the second derivative is negative. So use the concavity test to determine the concavity of the given functions on the given intervals. So on A, we take the first derivative as 2x. The second derivative is 2. So we have, this is concave up on the entire interval, on 3 to 10. Well, it's a parabola. Parabola is either all concave up or all concave down. On letter B, the first derivative is cosine of x. And the second derivative is negative sine of x. Now we want to know where negative sine of x is 0. Well, sine of x is 0 on 0 and pi. So let's put that on a number line. 0, pi, and 2 pi. So there's the possibilities of points of inflection. And we'll test pi over 2 and 3 pi over 2. So now if we plug pi over 2 into the second derivative, sine of pi over 2 is 1, so negative 1. This function is concave down from 0 to pi. If we plug 3 pi over 2 into the second derivative, sine of 3 pi over 2 is negative 1, but then times negative is a positive. So this function is concave up on that interval. So concave down on 0 to pi, and concave up on pi to 2 pi. The curve y equals 3 plus sine of x in example 2 changes concavity at the point pi 3. We call pi 3 a point of inflection of the curve. If the function is changing concavity, then that is a point of inflection. So it goes from concave down to concave up. Let's see, a point where the graph of a function has a tangent line, so it has to have a tangent line, and where the concavity changes is a point of inflection. A point on a curve where y double prime is positive on one side and negative on the other is a point of inflection. At such a point, y prime is either 0, because derivatives have the intermediate value property, or undefined. If y is a twice differentiable function, then y double prime equals 0. At a point of inflection, y prime has a local maximum or a minimum. Find all points of inflection of the graph of y equals e to the negative x squared. So the first derivative is negative 2x e to the negative x squared. The second derivative is first times the derivative of the second plus the second times the derivative of the first. And we can take out a negative, we can take out what? First time, yeah. Let's do this. Let's go 4x squared e to the negative x squared minus 2e to the negative x squared. And now let's take out, let's just take out a 2e to the negative x squared. So 2x squared minus 1. So now 2x squared minus 1, we want to know where that's 0. So 2x squared is equal to 1, x squared is equal to 1/2. So x is plus or minus the square root of, well, we can go 1 over square root of 2. So let's put that on a number line. We have negative 1 over square root of 2 and 1 over square root of 2. So let's test negative 1. We can test 0 and 1. So if we plug negative 1 into the second derivative, e over 2 over e to the x squared is not going to, that'll be positive no matter what. So we want to plug this negative 1 into this, which is 2 minus 1, which is positive, concave up. If we plug 0 in here, we get negative. And if we plug 1 over square root of 2, we get a positive. Oh, hold on. Make yourself at home. Check, check. Example 4, reading the graph of the derivative. The graph of the derivative function f on the interval -4 to 4 is shown in figure 4.26. Answer the following questions about f, justifying each answer with information obtained from the graph of f. A, on what intervals is f increasing? Well, this is the graph of f prime. F is increasing where the first derivative is positive. That's -4 to 2. So -4 to 2, and then 2 to 1, f prime is positive. So our justification is f prime is positive. On what intervals is the graph of f concave up? Well, we want to know where f prime is increasing. In other words, where the slopes of f prime are positive. 2 to 0. 2 to 0, and then 3 to 4. So 3 to 4. Now, how do I know that the graph is concave up? F prime is increasing. Letter C, at which x coordinates does f have local extrema? Well, certainly the endpoints. So x equals -4, x equals 4. Those are endpoints. And x is equal to 1 because f prime changes signs. That means there's a local extrema there. Letter D, what are the x coordinates of all inflection points of the graph of f? That's where f prime changes from decreasing to increasing, then increasing to decreasing, and decreasing to increasing. So x is equal to -2, x is equal to 0, x is equal to 3. F prime changes from increasing to decreasing or decreasing to increasing. And letter E, sketch a possible graph of f on the interval -4 to 4. Well, I don't know where f of -4 is, but it's somewhere. Now let's start way down here because we're going to, the function increases quite a bit. So the function increases and the slope of f prime is negative, so f prime is decreasing. This function increases concave down to 2, increases concave down to 2, and then it's still, the function still increases now, but the slopes are positive, so concave up to 0, so concave up to 0, and then still increases from 0 to 1, but now concave down, concave down. Now the function decreases at 1, concave down, decreases to 1, concave down, till we get to 3, and then still decreases, but the slopes are positive, so now concave up, like that. So the graph could look something like that. That's a possible graph. Caution, it is tempting to oversimplify a point of inflection as a point where the second derivative is 0. But that can be wrong for 2 reasons. 1, the second derivative can be 0 at a non-inflection point. And 2, the second derivative need not be 0 at an inflection point. So it goes both ways. If the second derivative is 0, it doesn't mean there's an inflection point. And if there's an inflection point, it doesn't mean the second derivative is 0. It could be undefined. Second derivative test for local extrema. Instead of looking for sign changes in y prime at critical points, we can sometimes use the following test to determine the presence of local extrema. Theorem 5 is the second derivative test for local extrema. If the first derivative is 0, that means we have a potential min or max. And then if the graph is concave down, then we have a local maximum. So if we have a potential min or max and the graph happens to be concave down there, there's a local max. If we have a potential min or max and the graph is concave up, then we have a local minimum. So local minimum, potential min or max, concave up, that's a local minimum. Using the second derivative test, find the local extreme values of that function. And we'll go f prime of x is 3x squared minus 12. We'll set that equal to 0. So 3x squared is equal to 12. X squared is 4, so plus or minus 2. Now instead of putting those on a number line and deciding that f prime changes from positive, negative, or negative, positive, we'll do the second derivative, which is 6x. Now f double prime of 2 is 12. That means this graph is concave up, and we have a local minimum. The second derivative at negative 2 is negative 12. That means the graph is concave down, so we have a local maximum. So local max of, let's see, I think I already got these values. 8, where's the max? It's at negative 2. So negative 8 plus 24 minus 5, that's 16 minus 5. Local max of 11 at x equals negative 2. And a local minimum of, let's see, a minimum's at 2, 8 minus 24 minus 5, negative 16 minus 5, negative 21 at x equals 2. Using f prime and f double prime to graph f. Let f prime of x equals 4x to the third minus 12x squared. A, identify where the extrema of f occur. So let's set the derivative equal to 0, and I can take out a 4x squared, which is x minus 3. So x equals 0, x equals 3. Identify where the extrema of f occur, x equals 0 and x equals 3. B, that's where they can potentially occur, I should say. Find the intervals on which f is increasing and intervals on which f is decreasing. So let's throw those values on a number line, 0 and 3. If I plug negative 1 into the derivative, we get negative. Plugging 1 into the derivative is also negative. And if we plug 4 into the derivative, 4 minus 3 is positive, so positive. So decreasing on negative infinity to 0 and 0 to 3, and increasing on 3 to infinity. Letter C, find where the graph of f is concave up and where it is concave down. Let's do the second derivative. Second derivative is 12x squared minus 24x. We're going to set that to equal to 0 and take a 12x out, and that's x minus 2. So x equals 0, x equals 2 are possible points of inflection. Oh, that's actually, that's possible points of inflection. Find where the graph of f is concave up and where is concave down. So let's go 0, 2. We're going to plug negative 1 into the second derivative. So negative times a negative is a positive, concave up. 1, let's see, 12 times a negative 1 is negative, concave down. Plug 3 in, 36 times 1 is positive 36. So concave down is 0 to 2. Concave up is negative infinity to 0, and then 2 to infinity. Sketch a possible graph for f, a possible graph. What are the critical points? The critical points are 0 and 3. We could have minimums and maximums, but 0 ended up being an inflection point. So I know the minimum is down here at 3. 1, 2, 3. I just got to get to, I got to have a minimum down there. Inflection at 0 and an inflection at 2. And from infinity to 3, we're decreasing the entire time. Now we're concave up from negative infinity to 0. So concave up, decreasing to 0. Then an inflection point, still decreasing. An inflection point at 2, but then we're bottoming out at 3. So there's that minimum. This is a possible graph of the original function. A function f is continuous on its domain negative 2 to 4. F of negative 2 is equal to 5. So they just give us a point. That's nice. Negative 2 is 1, 2, 3, 4, 5. F of 4 is 1. 1, 2, 3, 4 is 1. And f prime and f double prime have the following properties. From negative 2 to 0, the graph is increasing concave up. So increasing concave up like that. And then from 0 to 2, the graph is decreasing concave up as well. So decreasing concave up like this, let's say, right there. And then 2 to 4, we're decreasing concave down. So decreasing concave down like that, right there. Find where all absolute extrema of f occur. So one, we have a maximum at x equals 0 and a minimum at x equals 4. 2, find where the points of inflection of f occur. There's a point of inflection at x equals 2. 3, sketch a possible graph. I did that. That's how I answered 1 and 2.